So we have this model that's going to help us understand how a ship mast works. And we're going to start off by analyzing the dead loads. The dead loads are the self-weights of the structural members. And we're going to start off by looking at the column. The column is a strictly vertical structure. Its weight is transmitted down. It supports itself in compression, and it's not very interesting. It's not what we're here to look at. The cables connecting the structure have almost negligible weight, so we can put them aside. But the interesting structure here are the yard arms spanning horizontally out of the column, which are these structures, and we're going to focus on them and try to analyze how they work. So we're going to look at the support for the structure now. We're going to start off with the most obvious one, which is the fixed connection base of the column. It needs to be a fixed connection to give the structure its main stability. And we have three less obvious ones, which are the cables connected to the ship deck. And these cables act mainly to give the structure its lateral stability. So we have one cable acting in this plane, giving the structure stability if it tries to bend away from it. And similarly, this one cable acting in that plane. And the thing about cables is that they can only act in tension. So what would happen if the structure tried to bend towards both cables? So now we know that we need a third cable to support the structure in that direction when it goes into tension. Okay, we're going to start off by looking at this one member, this one yard arm, and see how it reacts under its own self-weight. Now, the yard arm, we can assume it has a constant cross-section, which can be modeled as a uniformly distributed load. And how we're going to go about this is we're going to loosen this one cable here, so as if it weren't there, and we're going to apply a load that's going to be the self-weight of the member. Now, what happens when we load it, as we can see, the diagonal cable, the diagonal cord, lengthens and gets tighter and tighter. And if we go back and we make it tight to start with, we make it tight initially, and we load it again, we can see that it would want to act the same way, and it would want to lengthen, but because it's restrained, it doesn't. It goes into tension, and that is how it helps support the self-weight of the member. Alright, so now we're going to look at the live loads, and we're going to use a couple of models to help us come to grips with how the cables and the yard arms help the mast in resisting the lateral loads, mainly from the wind. Okay, so here we have a model of the mast and the cables attaching it to the deck of the ship. Now, here we're only dealing with a two-dimensional plane, so we only have two cables. But in the real case scenario, we have a 3D plane, in real life a mast. So we'd have a cable spanning out of the plane, support it in this direction, stopping it from going forwards or backwards. Okay. So the mast in real life is going to be dealing with a lot of lateral loading from the yard arms. If we have a lateral load hitting the mast here, we can see how it deforms, and the cables act to resist that deformation, to resist the forces. So with this load, lateral load, we see that the right hand side cable tightens to resist the lateral load, and the left hand side cable loosens and does nothing. And if we load it the opposite way around, then we see the exact same situation but mirrored on this side. So we have the right hand side cable going loose and the left hand side cable tightening. To really appreciate this, let's see what happens if we take away the cables. Okay, now that we've removed the cables, let's see what would happen if we applied the same lateral load as before to the mast. For the same lateral load, we notice that the mast deforms a great deal more than when it was restrained by the cables, and this we can see that the mast behaves exactly as a cantilever would, with one fixed end and one free end, and that kind of beats the point of a mast where we need it to be rigid to resist the wind loads. The model we looked at previously didn't give a real life indication of the mast. See, the mast had yard arms spanning horizontally that were connected using cables to lower yard arms. Now, why do we have these cables? Now, if you imagine a yard arm applying a lateral force on this point, you can see as I apply force, we see no bending at the mast. Well, if I apply a horizontal force anywhere else, you can quite obviously see the deformation in the mast. And that's why the cables span between the end of one yard arm and the beginning of the yard arm above it. So any horizontal force is completely opposed by the horizontal component of the force in the cable. So the last part of the mast we have to analyze is torsion. Now, what is torsion? Imagine I am the mast and a force acts along this axis, along myself. And so if a force acts on this axis, then it's going to cause the mast to bend, whether it acts in any direction. But if we offset that force along another axis, for example, if it acts along my arm, then that force is going to make me want to twist. And this sort of motion is called torsion. So how does the mast resist this torsion? Now, if you take a closer look on the actual, this is the cross section of the mast. And we have a yard arm going out, and we have a force acting on it. Then the shear force will be transmitted through this yard arm, and it will go in loops around the cross section of the mast. And that is how torsion is resisted in shear. And the wider this loop, the bigger this loop, the more material there is to resist this torsion. Now, what would happen if we had a much smaller cross section? Then there would be less material to resist it, and it would have less resistance towards the torsion. So, to further illustrate this, we've had the guys at the lab working for 3 weeks to build this really expensive model that we're going to use to explain how torsion works. Now, have you ever heard of an Indian burn? Basically is this kind of motion. What we do is we're applying uniform torque on this expensive model. And as you can see, although it's flimsy and slender, it has quite good resistance towards torsion. But what would happen if it wasn't a closed section? What would happen if it was an open section and it tried to resist torsion? As you can see, it fails horribly. Alright, to explain this, we're going to draw another illustration. And if we have as opposed to a closed section, if we have an open section, what the shear force is going to do is it's going to form, because it's limited, it's going to form a much narrower, if you will, loop, because it has less material to occupy, and that is why it has less resistance towards torsion.